Good morning. I wanted to go through a few of the problems from the homework this week before you guys take your quiz. So please follow along with these problems. We're going to look at number 20, 21, and 47 in chapter 15. So number 20 reads as follows. Resonance on strings. So a violin sounds a note of F sharp with a pitch of 370 hertz. What are the frequencies of the next three harmonics produced by this note? So the concept here is that higher harmonics are whole number multiples of the fundamental. So if we know the fundamental frequency, we're going to know all of the harmonics. So the F sharp with a pitch of 370 hertz, we're going to assume that that is the fundamental frequency. And the next three harmonics are going to be 370 times 2, which is 740 hertz. 370 times 3, which is 1,110 hertz, and then 370 times 4, which is 1,480 hertz. Your textbook has a number which is slightly different from that, but that's wrong. Okay, number 21 is an important question. And there we go. Let me restart by reading it. We have resonance in closed pipes. One closed organ pipe has a length of 2.4 meters. So we're asked, what is the frequency of the note played by this pipe? So I'd recommend drawing a picture here. So we have a pipe open at one end. Our pipe length is 2.4 meters. And we know the relationship between the length of that pipe and the wavelength. And the wavelength of the fundamental frequency is going to be 4 times the length of that tube. Remember how we have a standing wave pattern, which is half a football fitting into that pipe. So we want to know what's the frequency here. So we're going to use the wave equation. Velocity is frequency times wavelength. We know the speed of sound is 343 hertz. And we also know the wavelength is 9.6 meters. So 9.6 meters, I got that by taking the length of the tube times 4. And we can solve for the frequency of this note as being 35.7 hertz. The second part of this question talks about beat frequencies. So we have a second pipe being played at the same time, and a 1.4 hertz tone is played. And so what we have going on here, the first expression is the beat frequency is the difference between the two source frequencies. And we're told here that the second pipe is too long. It says, by how much is the second pipe too long? So what that means is the longer pipe is going to produce a lower tone or a smaller frequency and have a bigger wavelength. So how do we figure it out? First we have to find the second frequency. We know our original pipe was 35.7 hertz. And we know the difference is 1.4. And so we're going to subtract 1.4 from 35.7 to get 34.3. So I knew that I should subtract in this case because I know I'm going to have a lower tone. And that should make sense. Longer pipes make lower tones. But basically, it's if we didn't know that, all we could say is that the second frequency was 1.4 higher or 1.4 lower, and then you'd have to, problem solve from there. So then we're going to use the wave equation. 343 hertz equals the new frequency, the slightly lower frequency, 34.3 times the wavelength of this wave. So the wavelength of this second tone is going to be 10 meters, and we need to find what the length of that tube is. So 10 is 4 times the length of the tube. So remember our wavelength, length of tube relationship. So 10 divided by 4, the length of this second tube has to be 2.5. Now we're asked by how much is the second pipe too long, so really we compare to our first pipe 2.5 to 2.4 meters, and so the difference in length is 0.1 meters. Number 47 is a Doppler effect problem. I'm glad somebody asked about this one. The Doppler effect, we're going to use this equation right here. So the frequency that we detect is the frequency of the source multiplied by the velocity of sound minus the velocity of the detector divided by the velocity of sound minus the velocity of the source. And before we get into that, let me just show you a picture here of how this might look. So we have in your book here a moving source. Okay, so we have the train with a velocity. It's emitting a frequency which is based on whatever the sound source is, but since that sound source is moving, it catches up with its own sound waves. So sound is a spherical wave. It goes out in all directions. But if I'm moving in one specific direction, I'm going to catch up with the own waves that I'm producing, in effect shortening the wavelength. And if I decrease the wavelength, I'm going to increase the frequency as per our wave equation relationship. So that's how it works. And if you go a little further with this, you can actually go faster than the speed of sound. And what you get in that case is if you're outrunning your own waves, you produce what's called a Mach cone. And you should look this up on the internet, what it looks like. But basically we have a wave front which ends up being an area of constructive interference from all the wave fronts that you're trailing behind. And it has a really large amplitude. And so the sound you hear from a supersonic jet, it's called a sonic boom. And it's going to be a really loud noise because of these concepts which I just mentioned. I'll probably have to show you a little video on that in class next week. Anyways, the problem we're looking at here, number 47, involves this train. So the train has a velocity of 31 meters per second, and its source frequency is 305 hertz, so it's a whistle. What's the detected frequency for a couple different situations? The first for a stationary train. And so what we're going to do is we'll say the frequency of the detector we observe is the frequency of the whistle on the train, 305 hertz, multiplied by the velocity of sound, so the velocity of the wave, this V here is just 343, minus 0. So in this first case, our velocity that we're detecting, we're stationary, so there's no motion. And we divide by 343 minus 31. 31 was the velocity of the train. And so we do that math, and this expression here reduces to 1.09. So we multiply our source frequency times 1.09, and we get a Doppler shifted frequency of 335 hertz. And so we need to check that answer to think if it makes conceptual sense. When a source of sound is approaching you, we should hear a higher than normal pitch. If the sound was moving away from you, we would have a Doppler shifted frequency, but it would be lower than the source frequency. And that all has to do with our relative velocities that we use in this equation. So the difference would be here if the train was moving away, we would have to switch the sign of this velocity term in the denominator. So these equations are, we have to sort of call moving to the right the positive dimension. So if the train was moving back to the left, we would say that would be a negative velocity, and we'd subtract a negative, so ultimately we'd add. This expression down here was sort of just another way your book showed that. I'm not going to go into that. I'll keep it simple with this first one here. So the second part of this, we have the velocity of the train is still going at 31. Same 305 hertz tone, but now the detector is moving towards the train at 21 meters per second. So our Doppler shifted frequency should be even higher. Okay, now we're really stacking those waves close together. So the frequency detected is going to be our original source, 305. And so we have the 343 plus 21 meters per second. So why did I do a plus there? This 21 meters per second is the velocity of the detector. And typically we go minus the velocity of the detector, but the detector is moving in the negative direction towards the original train. So if this is the train moving with a positive velocity, here's the velocity of the detector moving in the negative direction. So we're subtracting a negative value, so we add 21 meters per second. 343 minus the velocity of the source, which that remains the same as minus 31, will reduce this whole expression to 1.16. So our original source frequency, 305 hertz, multiplied by 1.16, is going to give us a Doppler shifted frequency of 353, which makes sense because that's even higher than the original from the first part of the problem. So, important concept here, the Doppler effect. I haven't really talked about that much. All right, good luck on the quiz today. I am done here, unless you have any more questions. But how would I have your questions? I'm just making a video. So, goodbye.